Okay, today we're going to be doing some past exam questions from the third midterm of Calculus 2 from 2013. The 2020 third midterm is coming up relatively soon. We've covered all the content that we need to know. Now let's try and solidify, do some examples. As always, the very best thing to do to prepare for the midterm is to do past exams and then focus on the things that you find difficult, work on the odd-ordered examples at the end of the book, at the end of the chapters of the book, and use my office hours for anything you don't understand. Okay, so let's start. This is question 1. We have the following. We have sequences AN and BN, and if we know that the sum n equals 1 to infinity Bn diverges, which of the following is guaranteed to be true? I need to look up how to spell guaranteed. Okay, so the first statement is that the sum from n equals 1 to infinity minus 1 to the n, an diverges. Sum n equals 1 to infinity minus 1 to the n, bn diverges is the second statement. The third statement is sum from n equals 1 to infinity an plus bn diverges. And the fourth is that the sum from n equals 1 to infinity bn minus an diverges. And the fifth is that an does not converge to 0. Okay, I like this question. This is an effective way to test your understanding. So let's get to work on it. What do we know? We have these positive terms, a and bn. We just know that bn diverges, so I like to represent this with a picture, of course. So let's do these blocks to represent the bn. Okay, so this is 1, this is 2, this is 3, this is 4, and so on. As always, we visualize this. And the height of the first block here is b1. The next height is b2, and so on. And our hypotheses are that the an are less than the bn. So, take a different color. So the an are these blocks that live inside, right? This is the an. These orange blocks. Okay. And we know that the sum of the bn diverges, so the area of all of these blocks from 1 to infinity is equal to infinity. So we have something with total infinite area as we sum together the area of all of these blocks. Okay, and what we've got to do is figure out which of these statements is true. All right, so looking at the first statement, we have that the statement that the alternating series we create out of the an diverges. Okay, so what do we know? We know that if we have positive terms and we make a series out of them, then they will converge if the terms go to 0 fast enough, right? The key example is 1 over n. 1 over n has a sequence of terms that go to 0, but it certainly doesn't converge, right? So example. 1 over n, and the sum n equals 1 to infinity an diverges. Okay. So going to 0 at the rate of 1 over n is not good enough. Yeah? But for an alternating series, we know that it doesn't matter how fast the terms go to 0, because we learned this, because we're simply going a sequence of steps forwards, backwards, forwards, backwards, forwards, backwards, forwards, backwards, forwards, backwards. And if the size of these terms just goes to 0, we are ultimately going to end up at some particular number at infinity. Yeah. So the fact that we have this an is less than bn actually means we have no restriction on how small the an have to be or how quickly they go to 0. And we're also creating an alternating series out of them. So this definitely does not need to be true. Right? This definitely does not need to be true. So to really sort of nail down that this doesn't have to be true, we have to come up with an example of an and bn for which this is false, and it's very easy to do it. We should take our bn to be what I called an right here. So let's take bn to be 1 over n. And then the sum of Bn diverges. So it satisfies the hypothesis. And then we can take An to be any decreasing sequence. We can even take it to be just equal to Bn itself. So now let An equal Bn equal 1 over n. Yeah? Then, sure enough, this thing, the sum of Bn, does not converge, it diverges. But we know that the sum of n equals 1 to infinity minus 1 to the n over n converges. Okay? So this example satisfies all of our hypotheses, but it's definitely not the case that the alternating series diverges, it converges. Okay? So we know the answer is no. All right, let's do the second one. The sum to minus 1 to the n Bn diverges. We can kill this with the same example, right? Because of the discussion we just had that if we have a sequence of positive terms, they have to go to 0 fast enough, right? These guys, Bn, do not go to 0 fast enough. Yeah? But if they go to 0 at any rate, and they're monotonically decreasing, then they definitely converge by the alternating series approximation or error approximation theorem. Right? So this is no. Take we can say let, so take Bn to be equal to 1 over n. Doesn't converge, but again, sum of n equals 1 to infinity minus 1 to the n over n does converge. And that's it. So that's definitely false. Okay, the sum of An plus Bn diverges. All right, now let's think. So this is our picture. The Bn are the orange blocks, the yellow blocks are the An, right? And if we consider An plus Bn, it's the orange block plus the yellow block, right? Which definitely lies above the orange block. In the language of maths, we have that Bn plus An is bigger than or equal to Bn, right? So if we take something which is bigger than this collection of green blocks, which actually contains all of these green blocks, and the area of all these green blocks is infinite, then for sure the area of that thing will be infinite, right? So if I put on blue like this would be the sum of An plus Bn. This is An plus Bn. Then for sure, since these blue blocks contain the green blocks and the area of these green blocks, as we sum from 1 to infinity is infinity, then the area of these blue blocks is infinity. So, and in the language of math, that's the so-called comparison test. So, by comparison test, the sum n equals 1 to infinity, An plus Bn diverges. So this is true. There's only one true answer, so at this point, you could just stop and say, okay, in the multiple choice, this answer is C. However, a very good idea would be to check the other ones, because you could be making some sort of mistake, some misunderstanding. And if you find another that you believe is true, then something's going wrong. Okay, so let's check it out. So this should be false. Bn minus an. So let's see. So Bn minus an, well, we could just take them to be equal, right? Because that still satisfies the hypothesis. So this is false. No. Let Bn be 1 over n and also be equal to an. It satisfies everything with the hypothesis, but Bn minus an is just 0 in that case, and if we sum 0, for sure it converges, right? So that's false. An does not converge to 0. This is definitely not the case, right? So what do we know? We have that an is less than Bn and Bn diverges, right? And so we don't know anything about an from this. We could have something which is less than a divergent series, which is converging or diverging, right? We just don't know, so it doesn't have to imply this thing converges to 0. And even if we had an diverges, we could still have that an converges to 0, right? So this is hopelessly false. So no, we could take Bn to be 1 over n, and then an just to be 0 for all n. Satisfies the hypothesis. An certainly does converge to 0. It's always equal to 0. Yeah? So what they're trying to somehow mix you up with is this divergence test. Let me remind you. If we have sum n equals 1, infinity an converges, then an, limit of an is equal to 0. Okay. And again, this makes sense from the picture. It doesn't require it to be a sequence of positive terms. Simply, if you have this infinite sum, it's doing an infinite collection of steps, right? And as we take a larger and larger number of steps and let that number go to infinity, we end up at some particular point. Now, that can't be the case if we keep doing big steps, right? If every now and again, doesn't matter how rarely, but every now and again as we go along the integers, we take a step of size, whatever, take a step of size 10 centimeters, then we're moved away from wherever we might seem to be converging to. Yeah? So the only possible way we can have something converges as a series is if the terms go down to 0. So formally in the language of maths, we just can use the fact that the definition of this thing is the limit of the partial sums, right? And if we take the nth plus 1 partial sum, that's just the am terms, and both those limits are the same as m goes to infinity. And that's equal to 0, so that's why. But all that is an expression, or in the language of math, of what I just said, that simply if we are doing an infinite sequence of steps, once again, it's just not going to ever end up in any fixed place as we allow more and more steps, if every now and again we take a decent sized step. And decent size, I said 10 centimeters, it could be half an inch, it could be anything. We simply can't converge if we're just going to do some sort of a jump away from wherever we are every now and again going forward towards infinity. So this is the divergence test, and something the examiners will often try and trick you with is the fact that the reverse is not true. So Reverse is definitely not true. Because we can have an is 1 over n, which doesn't converge, but the terms still go to 0. So going to 0 is not enough, right? Going to 0 is not enough. However, if you do converge, then you have to go to 0. And this is something that many people get confused with. This is even some sort of logical problem. The difference between A implies B and B implies A can be fuzzy for people who are not used to this kind of thing, but these are completely different statements, right? So A in this case is that the series converges. B is the statement that the limit of these terms is 0. It is the case that series converges implies the terms go to 0. But its reverse is absolutely not true. The reverse is absolutely not true. And another thing to know, or another thing to pay attention to, is that we got through this, and understood most of this, by having a good understanding of just one example. And that was the example of the sum of 1 over n. And that's often the case for this kind of stuff, and even for higher level math, even at level research. There's often some key example or key couple of examples that if you understand them very well, then the theory behind some part of math is pretty straightforward, because you can just keep comparing it to the example, right? So in this case, for a series of positive terms, the key example, or an absolutely key example, is this 1 over n. Yeah, so be very, very happy with the fact that this thing is a series that does not converge, but nevertheless the terms go down to 0, and we can kill many of these statements. All right, so back to the question. It's a multiple choice question. The only correct one is here, and that answers that. All right, let's do another question. Okay, let's do the second question. Consider the series S1, which is the sum from, I'm going to write k equals 1 to infinity of minus 1 to the k plus 1 over k factorial, and the series S2, which is the sum from k equals 2 to infinity of k over 2k plus 1 to the k. And then we have a bunch of multiple choice options which are asking, which we have to identify the true statement. It's statements like series S1 converges conditionally, series S2 converges absolutely. That's statement A. Statement B, series S1 converges absolutely, series S2 diverges, and so on. So basically we need to know if these series converge and in what sense, absolute convergence or conditional convergence. Okay, so solution. Let's recall what absolute convergence and conditional convergence means. So a series converges absolutely if and only if the sum of its terms, the absolute value, converges. So where the series is this thing, the sum n equals 1 to infinity an. Okay? So, absolute convergence, I have a video on this, is a strictly stronger property than just converging. So if we denote the series of things, the set of things that are series that converge is the outer blob, so series that converge, And the inner blob is things that converge absolutely. Okay. Then those guys here that do converge, but do not converge absolutely, converge conditionally. So I actually want to change color. Okay. All right, so we're going to have to determine what happens with these guys. And let's look at the first guy. So for S1, it's an alternating series, okay? But if we look at the terms k plus 1, try and write that better, over k factorial, those guys are going to 0 like crazy, right? That is an incredibly fast decreasing sequence, right? So notice that k plus 1 over k factorial, well, if we ignore the plus 1, then it would just be k over k factorial, and that would be 1 over k minus 1 factorial, which obviously goes to 0 like incredibly fast, right? It's very similar to a series that we know goes to 0 very, very fast. And so we can guess, and we'll be right, that this is going to 0 incredibly fast. So if it goes to 0 incredibly fast, and we take the absolute value of the terms, then it is going to converge still, right? Things will converge conditionally only if, when we take the absolute value, it no longer converges. So a classic example of something that converges conditionally, so example of conditional convergence, we build it up out of our friend, the sum of 1 over n. Convergence is this thing, the sum from n equals 1 to infinity minus 1 to the n over n. This thing converges, but it doesn't converge absolutely, therefore it converges conditionally, right? Doesn't look like that will be the case for here, right? If we take the absolute value, it's still going to 0 so incredibly fast, we expect it to converge. So our guess is it converges absolutely, yeah? And what's another giveaway? Another giveaway is the k factorial. If you have a k factorial and you've done a number of problems where you've put something with a k factorial inside the ratio test, you'll see that the k factorial simplifies dramatically and the thing will always converge because the ratio will go down to 0, right? Well, pretty much always. You have to really be inventive to cook up an example like this where you're dividing by k factorial and it doesn't go down to 0 when you take the ratio. So our guess is that it converges absolutely. We see a k factorial, we're thinking let's try the ratio test. Okay, because the ratio test is going to identify if the series in its bones goes down to 0, either like geometric series or even faster than geometric series, right? And this one looks like it's going down faster than geometric series. So we write a sentence goes to 0 very fast. So try ratio test. Let me write something that is coherent. So expect absolute convergence. Try ratio. So let's do that. So let ak be minus 1 to the k plus 1 over k factorial. So the absolute value of k plus 1 over k. What's going to happen? The minus 1s we don't care about. We are going to have k plus 2 over k plus 1. And then we're going to have k factorial over k plus 1 factorial. Right? And k plus 1 factorial is k plus 1 times k factorial. So that is k plus 2 over k plus 1, 1 over k plus 1. So it's k plus 2 over k plus 1 squared. And sure enough, this thing is going to go to 0 as k goes to infinity, because the guy on the top is of order k, the guy on the bottom is of order k squared, so the limit as k goes to infinity, ak plus 1 over ak is equal to 0, so converges absolutely. Okay, and that's it. It converges absolutely. We know this for sure. Yeah? So we have three possible options. It either diverges, it converges conditionally, or it converges absolutely. Yeah? And we know it converges absolutely. That's all there is about this series. Of all the possible options, that's all. That's all we can possibly know in the list of multiple choice options we're given. All right, let's look at S2. Change color. Now, a giveaway here is that we have something to the kth power. So the natural thing to do is to use the root test, because if we take the kth root of something to the kth power, then we're going to have a simplification. So use root test. So if we let ak be k over 2k plus 1 to the k, and we take ak to the 1 over k, we just get k over 2k plus 1. Right? Which we need the absolute value, but it's positive, so we don't care. And the limit as k goes to infinity, therefore, of ak to the 1 over k is just going to be the limit as k goes to infinity of k over 2k plus 1, which is equal to 1 over 2. Yeah? Cool. So, what does that say? It says that as we get larger and larger and larger k, then the kth root of the terms is more and more like a half. So, morally, it is like saying that ak is like 1 over 2 to the k, right? Yeah. And therefore, it is actually going down to 0 like a geometric series, like the geometric series 1 over 2 to the k. So this thing will converge, and it will converge absolutely. Yeah? It's a sequence of positive terms. So convergence and absolute convergence is exactly the same if we have our positive terms. So using by the root test, so strictly using the statement of the root test, since this limit is less than 1, then it converges. And the less than 1 is again because if it's less than 1, then whatever that limit is, it's like a geometric series of that number to the k. So by the root test, converges absolutely. And that's it. Okay, so both of these series converge absolutely, and that's this problem. So that was option D. Okay, let's do another problem. Okay, question 3. Suppose we have this power series, the sum k equals 1 to infinity of ak x to the k converges for x equals 3 and diverges for x equals minus 6. Then we have a bunch of true-false options. Should I write these down or not? Well, I'm just going to read them. Save time. So we have a bunch of statements of the kind: the series converges when x equals minus 2, the series diverges when x equals minus 2, the series converges when x equals minus 4, the series diverges when x equals minus 4, the series diverges when x equals minus 6. So all the statements of the form: the series, it'll either be converges or diverges when x is equal to, okay? And then we have a bunch of different possibilities. Minus 2, 2, minus 4, and then 6. No, both of them are minus 2. Sorry. All right. That's another fairly cool question. Let's do this. Solution. Let's try and represent what information we have. So we know that this thing, a power series, will have a radius of convergence, right? It's a power series centered around 0, so let's draw the real line. Here we are at 0. So there is some r where we will have things will converge. So I'm going to do this and this. This is going to be r, and this will be minus r, but it doesn't have to be an open interval. It can be a closed interval, so I'm also going to do this. Right? Because it could converge on the closed interval minus r to r, the half open interval minus r to r, the other half open interval minus r to r, or the open interval minus r to r, right? We have all of these possibilities. That's what we know, okay? And the hypotheses are that it converges when x equals 3, right? So it converges when x equals 3. So 3 has to be inside here. 3 could actually be equal to r, but it has to be inside here, yeah? And 6 has to be outside here, which also means that 6 can be equal to r, but is outside whatever interval we have, right? Be it open, half open, or whatever. So then we have these particular choice of numbers, right? We have these particular choice of numbers. So let's write down what we know. We know that since series converges at x equals 3, so radius of convergence r of c, denoted by r, is such that r is bigger than or equal to 3. We also know because it diverges when x equals minus 6 that r is less than or equal to 6. And that is all that we know about R. That's all the information we can deduce. Okay? But R is definitely bigger than or equal to 3. So when we are at -2, we are somewhere here, which is definitely going to be inside the radius of convergence. Oops, this side, this is -2. Okay. So we must converge when x equals -2, right? So, change color. So, we are certain must converge right? So the statement it converges at -2 is definitely true. The statement it diverges at -2 is definitely false. Yeah? Cannot possibly diverge at -2 because -2 is inside the radius of convergence. Yeah? What about at -4? Well, at -4, then we know much less, right? So -4, since the radius of convergence is anything between 3 and 6, at -4 it could be within the radius of convergence or it could be outside. So we don't definitely know anything. We don't definitely know it converges or diverges. Yeah? And at 6, then again it's not clear because the radius of convergence is less than or equal to 6. So it could be equal to 6. Right? We could have a closed interval -6 to 6, and therefore it would converge at -6, or we could have a half open interval at -6 to open interval 6, it would still converge. Or the radius of convergence would be something smaller than 6, or it could even be 6 and we have an open interval, right? So at 6 we don't definitely know anything, so I'm going to write that down. So at -4 we know nothing. Because could have anywhere in 3 to 6, okay, and at -6 we still know nothing because even if r equals 6, we could have any kind of interval of convergence. Of the form of -6 to 6, -6 to 6, -6 to 6, or just the open interval, -6 to 6, right? Any one of these is possible if r is 6. So if it's this one, then yes, it would converge. If it's this one, yes, it would converge. Otherwise, it wouldn't converge. And if r is less than 6, it won't converge. So we don't know anything from our hypothesis. So the question says, which of the following is definitely true? It converges when x equals -2. Well, yes. If x is -2, then since r is bigger than 3, definitely converges here. So definitely converges. That's what we said. That's true, no matter what r is. B, the series diverges when x is -2. Well, that's definitely false. That's definitely false. The series converges when x is -4. Yeah, as we said, that could be true, it could be false. We just don't know from the hypothesis. So it's not definitely true. the series diverges when x equals minus 4. The same reasoning. It's not definitely true. We can't tell. The series diverges when x equals 6. Not definitely true because of this example. So the only thing that's definitely true is that it converges when x equals minus 2. So that is option B. So only B is definitely true. Okay. Let's just do one. Four. The radius of the convergence of this power series. So the R of C of the sum from n equals 1 to infinity to n x plus 2 to the n over n squared is, and then it gives us a bunch of options. Okay, cool. So first thing to note is that this is a power series around minus 2. So this is x minus minus 2. And to find the rates of convergence, we use the ratio test, right? So we're going to let an be 2 to the n, x plus 2 to the n over n squared. If you have some experience of doing this, you realize that these polynomial terms, n squared, are just going to be unimportant when we take the ratio test, and they'll be determined by this 2 to the n, but we're about to find that out. So if we do an plus 1 over an, that's the value, let's see what we get. So we're just going to have 2, x plus 2, and on the bottom here we're going to have n plus 1 squared, and we are going to get an n squared here. Right? And so let's put it over here. That is the same as 2 x plus 2 n over n plus 1 squared. And if we take the limit of this, as n goes to infinity, of an plus 1 over an, this thing right here doesn't depend on n, it's just x plus 2, so we treat x like it's fixed for this purpose, and we just pull it straight out. So that's equal to 2x plus 2, and the limit as n goes to infinity of n over n plus 1. And as we well know, this thing is going to have limit 1. We just factor out n from the top and bottom, and so this will just be 2 mod x plus 2. And then the series will converge if and only if, say that again, the series will converge if this thing is less than 1. Okay, so we need two mod x plus 2 to be less than 1, which is equivalent to x plus 2 is less than 1 over 2. And it's just asking us for the radius of convergence, but let's actually find the interval of convergence since we're doing this. Okay, cool. So let's draw a picture. So here is 0, here is minus 2, and so long as the absolute value of x minus minus 2 is less than a half, we're okay, right? So what range will that give us? Well, we can go from minus 2 backwards by a half, which will give us minus 3 over 2, and then forward by a half, which would give us minus 5 over 2, I guess, right? Minus 5 over 2, right? So we don't know yet about the endpoints, but we know that the radius of convergence is a half, because this distance right here is a half, right? And we know that if we're strictly inside this interval, then we're definitely going to converge, right? So the R of C, the radius of convergence, is 1 over 2. Let's see what option that is. Which is option B. And if we were going to try and figure out the interval of convergence, then we'd have to check the endpoints. So for interval of convergence, which I abbreviate to IFC, convergence, let's check. So when we have x equals minus 5 over 2, then x plus 2 is going to be where is my brain? X plus 2 is the same as minus 5 over 2 plus 4 over 2, which is just minus 1 over 2. And if we plug that into this thing, then we will get the sum from n equals 1 to infinity 2 to the n minus 1 over 2 to the n over n squared. It's going to be an alternating series, but we don't care because we have an n squared on the bottom. So it's definitely going to converge. It's even converging absolutely. So from this, we already know what's going to happen when x is equal to minus 3 over 2. It won't be an alternating series anymore, but it's still going to be divided by n squared, so it's going to converge. But let's just check it out. So we're going to have the sum from n equals 1 to infinity, 2 to the n. So a half plus minus 3 over 2, this is a half. It's 1 over 2 to the n over n squared. So this is the sum. N equals 1 to infinity, 1 over n squared. This converges. Which converges. So, the I of C is both of those endpoints. So it's minus 3 over 2 to minus 5 over 2. Easy, right? So this is kind of typical of our midterms. These are not hard questions. These are straightforward examples, similar to the kind you've done in homework. Simply you have to get them right, which is kind of a pain for multiple choice. So if you're someone who, like me, tends to make small minor errors, you really get penalized in the multiple choice. And you have to practice. You have to practice this. You have to be very fluid and fluent with this in order to be able to do this under exam conditions and not make a mistake. So, as I tell my section all the time, you need to start doing the past exams, the problem exams, the practice problem, and be in good shape, be fully confident that we can do these kind of routine questions by the time of the exam. And then there'll be one or two slightly trickier questions that will differentiate the B students from the A students. And that's something which, again, you need to practice. If you want to be one of these A students, you need to do the harder questions. But most of it is just getting right these routine questions, right? Nothing to be scared of, nothing anybody can't do well at. Just be able to do this basic stuff, and you'll be fine. Okay.